ABC Calc students, this is going to be day 14. We're talking about something called the chain rule today. And as a quick getting started here, we're going to talk about a summary of our trig derivative rules that we learned about in the last lesson. So taking a look at the trig functions in the left column, see if you can quickly produce the derivatives in the right column. Now, these are derivatives that I'll say you're probably going to want to memorize, even though, the notes that we had definitely showed good ways to derive them. So I guess if you get stuck, you could always do a quick derivation if needed. But I would say you'd really want these accessible to you right off the top of your head as you get more practice with trig derivatives. So the very first one we have is sine, and derivative we saw was cos x. And the derivative of cos, therefore, is negative sine x. Don't forget about these co-function relationships, right? The derivatives of co-functions are going to be the negated form of one another, which is kind of nice in terms of pattern purposes. So then we've got tan, whose derivative is secant squared x. And then I went into the reciprocals. Cosecant, the derivative there is negative cosecant cotangent. Secant's derivative is secant tangent. And then finally, cotangent's derivative is negative cosecant squared. So I'm going to be honest with you guys. When I filled this in, when I filled in tangent, I actually jumped to the bottom of the list and then filled in cotangent next. Because I was thinking, okay, well, negate that co-function, and there's the derivative for cotangent. Similarly, if whichever one of these you're most comfortable with, like secant, I just know right away it's sectan. So then I can negate the co-functions of those and say that that's the derivative of cosecant, which is my quick reminder here, right? Don't forget about those co-function relationships. They really help to generate some of those derivatives a lot faster. The next question in your notes is actually something that I'd like to practice with. So it's evaluating a derivative of an absolute value function, specifically at x equals 0. So my recommendation here is we're going to try it, and then we'll go over it next time I see you in class. But I've given you a little bit of a hint. If you don't know how to get started, think about maybe splitting this up into some sort of piecewise situation. Okay, then you should be able to evaluate the derivative, specifically at x equals 0. All right, so let's kind of get into what we're doing today as far as the chain rule is concerned. Well, to develop the chain rule, we're actually going to look at some more trig derivatives, and we're going to make some guesses and some predictions as to the derivatives of these three examples at the top. So we have the functions y equals sine 2x, y equals cos 3x, and y equals sine of x squared. So I want you to really quickly here predict what you think the derivative would be for each of the following. So go ahead and take a minute to do that. I'm going to right now tell you what I think plausible guesses would be based on what you know up until this point. If you're following our rules for trig derivatives, the plausible guesses I would expect to see are that y prime would be, in this case, cosine of 2x, right? Derivative of sine is cos. So sine of 2x, the derivative there would be cos of 2x. Similarly, if the derivative of cos is negative sine, here y prime would be negative sine of 3x. And then finally, for y equals sine of x squared, we might think, oh yeah, well, sine's derivative is cos, so therefore this would be cos of x squared. Well, how are we going to check if we're correct with our predictions? Well, of course, we've got some n-derive on the calculator, right? So let's go ahead and in your calculator, make sure that you have all of your windows set up appropriately here. I'm actually still in parametric mode, so let me switch this over quick. In y1, we're going to wind up typing in, let's start with our initial function sine 2x. And then in y2, we're going to do n-derive. I'm actually going to do one more thing here. In y2, I'm going to type in what our prediction was just to kind of see if that matches what we have for n-derive, see if those two things are identical or not. So in y3, now let's do n-derive math 8. Okay, make sure you take the derivative with respect to x. Sorry if there's a glare there. Of what we have in y1, so alpha trace y1 for all values of x. I know that I'm already set to radian mode, but I want to double check my window. Maybe I'll look at this from like -2 pi to 2 pi. That's kind of a good window for trig stuff. And for your y min and y max, I'll shrink it a little bit. I'll go -5 to 5. And I'm not sure if I have this simultaneous or not. Looks like it does. Okay, right off the bat. Oh, now clearly you can see this, because that magenta is a little tough to see. Move it over a little bit. That actually looks better. Right off the bat, I know that our derivative is not correct, because I'm looking at where y3 is. Y3 is my kind of faint colored magenta graph there. And that does not match what our prediction was, which was cosine of 2x. Okay, so our prediction's in red, the original function's in blue, and I can see that the magenta graph is definitely not matching that. So we're going to have to readjust our guess and kind of think about what's happening there. But think about what that magenta graph's equation is. Okay, we'll come back to that in a second here. All right, let's kind of adjust it for what we have in our second guess for cosine of 3x. So if I switch this to cosine of 3x, our guess was negative sine of 3x. And we don't have to change what we had for y3, because that's just going to end derive what we now have as our new input to y1. So if I hit graph here, oh boy. All right, those three things, again, definitely are not lining up. So I'll let this finish out for a second here, but let's start thinking about what is the actual derivative then. Our guess was negative sine 3x, but this graph that's in magenta here is not representative of that. If you're looking at my graph right now, what's in red was our guess. That's negative sine 3x. So it kind of looks like the magenta n-derived graph is an example of a negative sine function, but the major difference that we saw in the last two examples is that amplitude, right? There's definitely a big stretch going on here as compared to what we have in our guess. And in fact, that stretch, if I look at the height on the y-axis there, it's a stretch of 3. So instead of having that the derivative is negative sine of 3x, we should really have the derivative as negative 3 sine of 3x. Okay, that's the true derivative of cos of 3x. And if I just go back real quick over here to get sine 2x again, I'm going to adjust that real quick. And our guess was cosine of 2x. You know, we saw that wasn't the case, but what is this magenta derivative here? It doesn't wind up being cosine of 2x, but if you can see it kind of faintly on your screen, if I zoom in, it'll be better. Looks a little bit better. It looks like actually this is still a cosine graph that we're sketching, but it's with an amplitude of 2 for its max height. So in fact, what we should say for the derivative is not just cosine of 2x, but it should be 2 cosine of 2x. Now, I think the graph for the last one's going to be a little tough for us to determine, but where is this extra 2 coming from, and where is this extra, I guess in this case, 3 coming from? Well, I want you to think about the fact that the derivative of 2x and the derivative of 3x are respectively 2 and 3. So if we come back up to what we were taking cosine of this quantity, and originally, sorry, cosine of this quantity, sine of that quantity. The outside part that we're multiplying by is the derivative of what was on the inside of this function. So if you made that connection there, what's going to happen in the last case is we're not just going to get cosine of x squared, but it's going to be multiplied by the derivative of what's on the inside there. And that inside part, x squared, the derivative would be 2x. So go ahead for the last one, write 2x, and then you can write cosine of x squared. Okay. So hopefully that quick little n-derive was enough for you to help see that pattern, but it's really explicitly stated below in what the chain rule is. So what is the chain rule? It's really derivatives of a composition of functions. If we have a function h of x that's represented by g of f of x, how do we find its derivative? Well, to find the derivative of a composition, you find the derivative of the outside function first, but keep what's on the inside. right? So if we go back to sine 2x, the derivative of the sine function is cosine, and we keep that inside the same, 2x. But then you have to multiply that by the derivative of the inside. Well, the derivative of the inside here is 2. Right? Similarly, up here's sine of x squared. The derivative of the outside would be cosine of x squared. Keep that inside part. But then the derivative of what's on the inside, x squared, is 2x. So you can see how we can now start doing some more complicated derivatives when we have a composition of functions that's represented. So at the bottom here, it says if y is a differentiable function of u, and u is a differentiable function of x, then y is a differentiable function of x such that this would be true. We can find dy dx by calculating dy du. Okay, that's like the derivative of the outside function times the derivative of the inside function, du dx. So we're going to start by breaking this down by looking at compositions of functions, by looking at their two components, looking at kind of what the big picture is on the outside function and then kind of what's on the inside, and getting some practice here. So for the first example, we have y equals u squared, and u is equal to 4x cubed minus 1. So in order to calculate the derivative here, first and foremost, what is y equal to? Well, since u equals 4x cubed minus 1, I can replace it right here and say that we have 4x cubed minus 1 squared. And we actually have other ways of finding this derivative. I can definitely square this quantity, expand that out, and use the power rule to find the derivative there. But what's going to go a little bit faster for us is we just saw that since y is a function of u and u is a function of x, both of which are differentiable, we can find dy dx by doing dy du times du dx. Okay, and all of these are not necessarily fractions. These parts definitely cancel out, right, to leave you with dy dx. So hopefully that makes sense as kind of a process here. So what would dy du be? Well, dy du is the derivative of this function with respect to u, so that's going to be 2u. And then finally, du dx is the derivative of this function with respect to x, so that's just going to give you 12x squared, right? Derivative of the constant is just going to be 0 there, but we do get 12x squared. So what does dy dx equal? Well, remember that u is really 4x cubed minus 1. So you can come over here and replace that u with 4x cubed minus 1. Then if you want to clean things up a little bit, maybe take the 12x squared out here and multiply it by the 2 to get 24x squared, which you can then distribute into 4x cubed minus 1 to get your final answer of 96x to the 5th minus 24x squared. Okay. Now, I really think that the chain rule will be the way to go eventually for things that look like this, because I know we can square this quantity easily and then use that power rule like I suggested, but when the exponents get large, like if I said, hey, to the 10th power, find the derivative, I don't want to have to write that out 10 times. Chain rule is definitely going to help us in that situation. Let's try another example here. So if y is equal to sine x, but x is equal to t squared minus 4, what's our function y really equal to? Well, we can express y as a function of t by writing this as sine of the quantity t squared minus 4. So what would dy dt equal? Well, dy dt in this case is going to be the derivative of y with respect to x times, in this case, the derivative of x with respect to t. And you can see how when those dx's cancel, you are just in the end left with dy dt. All right, well, dy dx is cosine of x. Dx dt, in this case, the derivative of this is just 2t. Now, remembering that x is really equal to t squared minus 4, we're going to replace that in this function right here to get cosine of t squared minus 4 times 2t. And I would say typically we would probably bring this 2t in front of the cos function to write our final answer as 2t and then cos of t squared minus 4. So in terms of breaking these functions apart, more commonly, you're going to see this given at the start, right? This is already a composition of functions. It's the composition of the function sine x and the function t squared minus 4. In fact, that's why you had a lot of practice with this on your summer homework, is really thinking about how do we break apart a composition into two parts such that we can analyze what this chain rule is all about. But now that I think we have a good handle on this, you'll notice in the next one, I haven't really defined what the two separate functions are that compose make y equals tan of x squared. If you want to do that and break it up into two parts, we have really the function like tan x and then the inside part x squared. But I think if we just apply the chain rule here, we're going to find the derivative of the outside function, which is tan, and then just multiply that by the derivative of what's on the inside, which is the x squared part. Let's talk about the derivative of tan. So hopefully you're remembering that the derivative of tan is secant squared. So to find dy dx in this case, you're going to write secant squared of the inside, so keep the inside the same. And then the last step is multiply it by the derivative of the inside, which is pretty easy in this case, and just 2x. So the derivative of tan of x squared is 2x secant squared of x squared. And that's it, we're done. Remember that you can really check any of these using nderive on the calculator, so if you're unsure, go ahead and do it that way and make sure that what you think the derivative are in the actual derivative, if you do nderive, that those match identically. Okay. Moving on to the back. Let's take a look at sine squared of x. So for sine squared, you just have to be a little bit cautious that we think of this as being the function sine x squared, right? Notationally, these two things mean the same thing. So the outside function is kind of like a squaring function, right? And then the inside function is the function sine x. So it's almost like a composition of the function like u squared, but then u is equal to sine x. So to find dy dx altogether, the derivative of the outside would be if I use the power rule 2 times sine x to the first. All right, think of this as just any function, anything squared using the power rule would break down to 2 times that function, in this case to the first power now, when we decrease by 1, times the derivative of the inside. So the derivative of the inside would be cosine x, and therefore the derivative of sine squared x, which is the same thing as sine x squared, would be 2 sine x cosine x. Okay. If at any point you're feeling pretty confident and you want to try some of the rest of these, feel free to do so. Okay, I'll at least do 5 and 6. And then 7 I want you to try on your own, even though it might be the toughest one on the page, I think you can handle it, all right? What I think is going to help for number 5, you have a couple strategies here. You could use the quotient rule if you want to, but since we've proved the power rule for negative exponents, why don't we actually just transfer this to cosine of x to the negative third power? I think that's just going to help for our purposes of finding this derivative, so we don't have a chain rule within the quotient rule, right? So then how would I apply the power rule here? It's going to be negative 3 cos x to the negative fourth, right? The derivative of the outer function is this power rule. And then find that times the derivative of the inside. Well, derivative of cos is negative sine x. Now, certainly we'd want to clean this up a little bit. You know, if this is a multiple choice question, find the derivative of 1 over cos cubed. It's very unlikely that you're going to see this as the answer. So negative 3 times negative sine, we can actually write that as just positive 3 sine x. And then if we re-express this with a positive exponent, cos to the fourth x is just going to go in the denominator. So it's going to be 3 sine x over cos to the fourth x. Okay, so that's the derivative of 1 over cos cubed. All right, last thing I'm going to do with you on this page is, like promised, I'll do number 6, and then I'll let you try number 7. So for number 6, we have 2x cubed plus 1 to the fourth. So to find the derivative, think of this as the outer function being a function to the fourth power. So using the power rule, it's 4 times the function, 2x cubed plus 1, now to 1 less degree to the third. And then times the derivative of the inside, which would be 6x squared. If I'm being honest, I really don't want to expand what this cubed is right now. So the only thing maybe I'll do is clean this up by multiplying those two together. So that's 24x squared out front of 2x cubed plus 1 cubed. But I'll kind of stop there for now and say, yep, we're good to go. We don't need to practice with the algebra there. Okay, so like I said, I am going to have you try number 7, but I do think it's a little bit tougher than the others. So think real hard about this one. Of course, we're going to be using the chain rule here, but maybe as a quick hint, it's going to use the chain rule twice. Sorry if you're somebody who doesn't like me giving away hints here, but for those of you that do like hints, might be a chain rule twice. Okay, on the last page, let's talk about the AP exam. Here is a sample question from an AP exam from 1984, a really good year. Why was it a really good year? Mr. All was born. That's exciting. I love seeing. We'll go over it in class tomorrow. I'm still going to request that you take a look at this example and try it, but I'm going to reveal the answers in the video. So if you have questions about this, of course, you'll be able to let me know the next day in class. But as far as trying this, I do want you to hit pause, try this example, parts A, B, and C, and then I'll show you what I have as answers in just a moment here, okay? All right, so taking a look at this example, the first part is stating whether or not the function f of x that's given up here over this interval is even or odd and justify your answer. Well, hopefully you're remembering that even means it has y-axis symmetry and odd means that it would have origin symmetry. And there's certain tests that we do to help confirm that. So I did f of negative x. F of negative x winds up equaling this when you replace x with negative x. If you're wondering why sine of negative x is the same as negative sine x, it's called a negative angle identity. Cos of negative x, on the other hand, is the same thing as just positive cos of x. It's really because in quadrant 4, which is where the angle negative x terminates, in my opinion, as long as x is acute, cosine's positive in quadrant 4, but sine would be negative there. So when you kind of rewrite these without the negative x on the inside, sine gets negated, but cosine doesn't. All right, what does negative f of x look like? Negative f of x is just the negated form of the original function. And if f of negative x and negative f of x match, that indicates that we have origin symmetry, which means that f of x is an odd function. Okay, so hopefully you're able to confirm that algebraically. Okay, part B, find the derivative. Well, we should be really good at finding the derivative at this point, because what do we know? We know trig derivatives and we know the quotient rule. So I'm hoping that you applied all of those ideas into one, low d high minus high d low over low squared. So that's what we got here, cosine times 1 plus cos, derivative of the top, minus the high function times the derivative of the bottom over the low function squared. All right, so distributing the cos here and distributing maybe a positive sign into this eventually gets you this up in the numerator. And hopefully you're recognizing that you can combine sine squared plus cosine squared into 1. So here's what we found for the derivative. Cos plus x sine x plus 1 over cos squared when completely simplified. And finally, the last part says write the equation of the line tangent at x equals 0. So we first have to find the slope at 0, f prime of 0. When you substitute that into your derivative, you should find that that's 2. Right, cos of 0 is 1. Sine of 0 is going to be 0 anyway. And then, since f of 0 equals 0 for the original function, the equation of the tangent line winds up just being y equals 2x. You know, in terms of an AP question, I really think this is definitely within our wheelhouse of really getting a solid understanding of what's going on here. You know, it's all skills that we should be really familiar with in terms of finding derivatives, equations of tangent lines. Hopefully that worked for even and odd just at the beginning, kind of went okay as far as that testing was concerned. But if you have any questions about this example in particular, you'll let me know next time I see you in class. So that's the chain rule, guys. We'll be doing a lot more with chain rule in this class, so let me know if you have any questions.